In this video, we're going to talk about types of chromatography and exam-style questions. This is the video where you can do the questions, so stop the video, for example, do the questions. But in some examples, you have to actually measure the distances on the questions, so better off just watching the video and then trying the relevant exam-style questions on the attached worksheet. Now, RF and identification. You have chromatography and a student has wants to identify an amino acid. It's two TLC chromatograms, which we'll show you in a second, in two different solvents, A and B. Okay, what is the RF value of tryptophan in solvent A? And identify the unknown amino acid. Explain your reasoning. So here we have your two different chromatograms, and they're in two different solvents, solvent A and solvent B. And we've got our unknown on both of them, and you can see our unknown is here, okay, and again in a similar position on the other side. Let's get some space and start going through the questions. So the first one, as we've highlighted, is the RF value of tryptophan in solvent A. So we're going to use solvent A here. We get our ruler out and we draw our arrow. You can see here that we're going to the middle of this dot, that's the really key point, and going down to the baseline. And we measure that and we find, if we put it into RF calculation, that it's 32 millimeters. We then do the next thing is the distance moved by the solvent, which is the baseline to the solvent front. Just move our ruler over and we find that's 50 millimeters. And that gives us an RF of 0.64. And that's our answer to our first question. So let's put that over there. So we've got our first one. Let's move to our second part of the question. Identify the unknown amino acid and explain your reasoning. Well, what you're looking for is for the samples, the dots, to be on the same level. So if they're on the same level, they're most likely to be the same compound, okay? Not definitely though. So in this question, you've got two different solvents, so you're going to have to do two different comparisons. So first of all, if we look across here from the unknown, we can see that it could be glycine or isoleucine. So in the first one, the unknown amino acid could be glycine or isoleucine. Next one, we're going across here and we've got our unknown amino acid going across. Could be tryptophan or it could be isoleucine. And you can see that isoleucine is in both. And because isoleucine is in both, which you would have to explain, the amino acid must be isoleucine. And that is how you identify an unknown when you've got two different solvents. You just look across and see what is the comparison between the two solvents, which one is at the same level on both solvents. Our next question covers the effect of the solvent on the RF. So we've got RF values for different amino acids in a solvent, and we're not telling you what the solvent is. So because we can't tell you what the solvent is, you can't really talk about specific intermolecular forces, but we'll talk a bit more about that later. You identify the amino acids on the chromatogram using the data, and that's what they want you to do. And the second chromatogram is run using a less polar solvent. Predict the effect on the RF and explain your reasoning. Now our data is given here, so you can see we've got 4 amino acids and 4 RF values and a TLC plate. So let's move this to the side and then highlight the question we want. We want to identify the amino acids on the chromatogram given the data that we've got. So the first thing we have to do is do the RFs. Now I am showing you a ruler here so you can do it yourself. So if you want to stop this film at this moment and then do this, please do. However, what you do is use your ruler, go between here and here, find your baseline to your solvent front, and then also go from your baseline to the middle of the spot. And you've got your first one, which is 0.5. You do your second one, okay, and then you get 0.75. So we've identified our two RFs. All we have to now do is get rid of the ruler and then apply it to the table. So let's do that. Okay, so we've got rid of the ruler, and we now know it's histidine and leucine, okay, because they have matching RFs. So you're looking for that matching RFs. Let's go on to the second question, which is predict the effect, if any, on the RF values of the amino acids. Now this is about understanding, okay, so it's a really, really important that you understand the next part. So really important, our exam tip is polar dissolves polar and non-polar dissolves non-polar. So what does that mean? Well, it means basically if you have a polar substance, like a polar substance that you place on the TLC plate, the chromatogram, for example, like an amino acid, which are polar, and those amino acids have carboxylic acids and amines on them, both of which are very polar, okay, and they can both take part in hydrogen bonding as well. Okay, so if you do that, the polar will dissolve the polar. So if I have a polar solvent, then it will dissolve the amino acids really, really well. So what that means, because it dissolves the amino acids really, really well, it's almost like it's taking the amino acids up the plate. So remember, the solvent goes up the plate and carries these substances up with it. So basically, if the polar solvent dissolves the amino acids really well, it's like grabbing hold of these and dragging them up. Okay, and it's because of this relative solubility. It's the fact that this polar substance is dissolving really well in this polar solvent. And so we would expect the spots to be higher up if we had a polar solvent. But, okay, that means, in turn, that the RF would be high, because the closer you get this spot to the solvent front, the closer you get the RF to 1. Okay, so for example, this is 0.75, this is 0.5. It gets higher as you go up. So if we look at the question says, this time we're having a less polar solvent. So we just have to think, right, okay, if a polar solvent dissolves a polar substance really, really well and takes it out the plate, then a less polar solvent is not going to dissolve the amino acid because it's polar as well, which means those spots are not going to be taken up the plate very well because they're not dissolving very well. So they'll be somewhere here. So let's put them somewhere here. Again, we don't know the exact effect, so we're just doing this for an example. Let's just prove that the RF has gone down. So if you measure the distances, you'll get histidine at 0.13 RF and you'll get leucine at 0.25. And you can see they've gone from 0.5 to 0.13 and from 0.75 to 0.25. So they've reduced a lot. And I'm just showing you that to give you a clear example. Now, let's do the actual answer to the question. So, first thing is, the RF values would be smaller because the amino acids are less soluble in the less polar or non-polar solvent, and so would travel less distance up the plate. That's our kind of exam answer. Okay, but what I want to show you as well is that in this question we have only given you solvent C. So we haven't told you what the solvent is. Now, if I give you what the solvent is, so for example, I give you a specific solvent, for example, water, ethanol, then you can talk about intermolecular forces such as hydrogen bonding, and you have to add that to your question. So if you're doing the answer to this and you're given a specific solvent and you've got amino acids, for example, they will hydrogen bond with it, and that's their attraction. So you must mention hydrogen bonding as well. If in this question you're just given a solvent and you don't know what it is, then you don't need to do that because you don't know what the solvent is. But if they give you a solvent, please mention your intermolecular forces as well. Our last exam style question is about limitations and reaction monitoring. So we're going to explain how to monitor reaction using TLC, and we're also going to talk about what are the limitations. So first of all, there's a reaction given. Now this reaction given is propanol and acidified potassium dichromate. It doesn't matter, it can be any reaction that gives a mixture of different products or has different reactants. The organic portion was placed on a TLC plate after it was neutralised. You produced a chromatogram. As you can see, it's got 3 different spots on it. Okay, and TLC is going to be used to monitor the reaction. So how do you do that? So they want you to explain how to do that. And they want to make you explain how it's gone to completion. So the student runs the TLC in a different solvent and sees only 2 spots. And this is the reaction underneath. So you've got a primary alcohol going to an aldehyde going to a carboxylic acid. Okay, and hopefully you should know that from your alcohols section. Now let's put this to the side and look at the first type of question. Explain how the TLC can be used to monitor the reaction. So here we have, this is how you do it. So what you do is you take the reaction mixture, put a spot there, and then you'll put a spot on each baseline of your reactants and your product. So here is my reactant, okay, and here is my first product, propanol, and here is my second product, which is propanoic acid. And what I have to do is look at my chromatogram here, okay, and I have to look at it and go, right, okay, what have I got in here? Has the reaction gone to completion? So the reaction hasn't gone to completion because I still have propanol. Can you see same level? And I still have propanol, same level. So this has not gone to completion at this moment. Now, if I did this chromatogram again at a later date after I'd reacted it for a bit more time, then maybe once this spot had disappeared and this spot had disappeared and I just had propanoic acid, then I would be absolutely fine and I'd say it's gone to completion. Anyway, so let's move that up and just say, how do you monitor? Well, you monitor it by taking samples from the reaction mixture at regular intervals, run it on a TLC plate alongside your reactants and your product. And then you'll know when you only have your product. Let's look at the second question. The student runs a TLC in a different solvent and only sees 2 spots, suggests why there are 2 spots. So, the first thing is, compounds can't disappear. So, there are 3 different compounds here, 2 compounds here. No, they're not. There are still 3 different compounds in this sample. You put the same sample here as you have here, so there will be 3 different samples here. That must mean that one of these spots in this new solvent is at the same RF as another spot. Okay, it just means that 2 of the compounds have the same RF value, because that is a limitation of TLC, and that is why industrial chemists and research chemists, as I was before I became a teacher, have to formulate different solvent mixtures to make sure that they separate all of their products from their reactants, to make sure everything is separate on the TLC plate. Because on some solvents, you'll find that you can't separate the different parts. And if you can't separate the different parts, you can't use TLC to monitor. So it does have limitations, but it's limitations we can get round as chemists. We just need to find the right solvent to do the right